Hello, 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 Cal, Joshua. Are you ready?
Yes, I am ready. Can you see the
I
screen?
will
Can you see
give
the
some
presentation?
very brief opening introduction, and uh then you can start to show. Uh,
All
I
right.
just need just 1 minute. Okay.
Okay.
Hello everyone. I'm Tiny from Upchain, Chinese-speaking Web3 developer community. Mm, I'm pleasure to have Joshua at Open Course to show run powerful apps with the best execution environment. Uh, Open Course, just like the name, is an online open course. We focus on blockchain technology. Open course organized by Upchain, Dunlian, and Chinese, Rebase, and the Open Build community. Welcome, Joshua. Okay, let's start.
Okay. So first of all, hello everyone. It's very nice to be here. My name is João. I'm leader developer advocate for Cartesi, and I'm gonna be introduced and talking to you about Cartesi. The name of this presentation is Run Powerful Dapps. With the best execution environment, right? Why do we call this presentation Run Powerful Dapps with the best execution environment? We're gonna go through it during the whole presentation. But I think the important thing to grasp, the important thing to understand is that there are many ways to run your applications on Web3, on blockchain as a whole. And we think we figured out the best way to do it, the way that gives you the most flexibility and the way that gives you the stronger execution environment in the sense that you can run applications that are more complex. You can run applications that are able to do things that others are not. So one of the things that we can do, and we actually did a few times, and I always like to start presentations talking about this example because it allows you to see how complex it can be and how cool it can be, is running Doom on chain. Okay, so what happened is a long time ago, I think it was beginning of beginning of 2023, if I'm not mistaken. So that's more than 2 years ago, which is a century in Web3 essentially. But what happened is some people were discussing if Ethereum is the world computer, how come no one was able to run Doom on it? Because Doom at this point is almost a meme in where people run Doom on everything, right? They run Doom on Minecraft, they run Doom on Notepad++, but no one was running on Ethereum. So what we did was showcase how you can actually run Doom in our environment, log the whole gameplay. So every instruction while you're playing the game is recorded, and then you can verify your gameplay on chain. So yeah, Cartesi allowed for that, and it was one of our flagship projects. Rives is online, so if anyone is curious, you can visit rives.io. It's rives.io, and you can play not only Doom but a bunch of other games, and you can compete, and your gameplay is recorded and completely reproducible on chain. So it's a very nice experience, right? But how did we do that? How did this whole magic happen? And here's what I like to start talking a little bit about what is the execution environment on Web3. So the execution environment is not the application itself, is the host that is running the application. For example, whenever you're using any kind of application on your computer is the execution environment for that. and it has a lot of things going on for them. The first and foremost responsibility of the execution environment is being able to change the state of your application. That means if you have a given state, if you are in a web page, for example, and you make an input, or that means you click a button, you type something, then you change the state of that application. It's in a different state. It's simple enough. But to actually make a good one, you have to consider a ton of things. You probably need an operational system, or at least a basis where to run. You probably need to decide what kinds of applications you want to run inside your execution environment. So when you're picking your execution environment for your application, I think it's important for you to think all of this huge list of things. I'm gonna try to go at them one-on-one, but if it gets too extensive, I'm gonna skip them, right? So you have to think what kind of dApps or smart contracts, in case of Web3, are you optimizing for? Will your dApp perform lots of computations or just simple state transitions? Do you want developers to code their apps using Solidity, using Cairo, using Rust, using Python, or all of them? So your preferred programming languages are very important here. And then you have to think about developer resources. Are you offering introspection? That is your application able to see itself? Do you want containerization so you can distribute your application easily? You can distribute whatever runs inside your execution environment. So some of this context can get really complex. But the whole idea is that, like, latency tolerance, do your application needs to be extremely fast? Do you need extremely fast finality? Are your applications shared or isolated? That means will more apps be running in the same execution environment? That's all some sort of craziness that you have to think about when you're picking your execution environment. So we tried making an execution environment that kind of fits all these bills and is as flexible as possible, so you can use to create your applications and your applications can run on them, right? We wanted to make the best execution environment possible. So that's why we call it BEE, best execution environment. It's essentially a B. And we had some requirements when we wanted to create this execution environment for your apps on Web3. So we wanted it to have a full CPU for itself. We wanted it to not compete for block space. A long time ago, there was this, once again, not that long ago, a few years ago, there was this event where the CATS application, I don't quite remember its name right now, but it basically broke the base layer because of so many transactions being sent to that. And no other application was able to compute because that app was taking all the resources of the blockchain. So we wanted the applications to have a full CPU for themselves and not compete with resources with other applications. We wanted it to be more flexible. We wanted it to be familiar, so people wouldn't be restrained to just Solidity. But we also did not want to create just one language, so people would be restrained to that language. So I think if we were pivoting from Solidity, we wanted to give the full flexibility that someone always has. And then we wanted to have backward compatibility, so people could use things they were already used to. They could use languages they already used to. And that's when we started realizing that Linux would probably be the solution, right? Everything we were describing was essentially Linux. And Linux brings some advantages in terms of everything that is built for Linux, but it also brings some disadvantage, which is the theoretical overhead that you have to spin up a node that runs Linux? Well, we kind of solved that pretty fast with holding the state of the machine with the Linux already loaded. And when you spin up a new node, you already start from a snapshot. So you don't even have that overhead, which makes things easier. But what I want to say is everything that we put in this execution environment while we created it, we decided to keep it simple. So there were some decisions that we made that were in order to make people feel like they don't need to learn so much when coming into Web3. You want to code with Python, you can code with Python. You want to code with Go, you can. Rust, you can. C++, also, you can. You're free because you're in a very familiar environment where you run the same things that you always run on Web2 as well, right? So I love the story of the space race, where one side was developing this whole complex pen that would be able to write in zero gravity, because in zero gravity, the ink cannot actually write to the paper because it's actually tarnishing the paper while it writes, but in zero gravity, it wouldn't get stuck to the paper. And then they created this whole technical solution. They spent billions of dollars on it. And the other side just figured they could use the pencil to take notes on space. So I love the idea that sometimes simplicity is just the best solution and the cheapest solution, and it saves everyone's lots of headaches. Another example of that is Indiana Jones. There is this scene in the movie where the guy is showing all his skills with his sword, and Indiana Jones simply uses a gun and wins the fight. So sometimes, yes, the gun is much more complex than sword, but to make something good with the sword, in this analogy Solidity, right? You have to put a lot of effort to it. And sometimes you can just use the simple tool. So when I talk about Solidity, I think that Solidity is a great tool. I like to compare it to a plier. You can do a lot with it. You can bend things, you can cut things, you can hold things, you can even hammer things with it. But when we are talking about where we want to get to an environment where you have all the tooling available for you, all the tooling that you ever used and all that is flexible. So with Cartesi, you can essentially use OpenCV, you can use scikit-learn to create machine learning applications, PyTorch, you can use SQLite to hold data, you can code solutions in Python, in C++, in Go. You can do, honestly, whatever you want, and this is pretty awesome. So we created this machine, which is called the Cartesi Machine, as you can see the name here. And the Cartesi Machine is a RISC-V emulator. So we took all the instructions that RISC-V, which is an instruct set architecture, uses, and we were able to create this virtual machine per se. We like to call it emulator. And in this emulator, we were able to install Linux. But we also made this RISC-V emulator deterministic with some attitudes that we took, like we stopped the clock, and the clock only runs when it's actually executing. We cut access to the internet. So that means there is no external interference. Inputs only arrive through the designated channel. We also left only one processor, one CPU, so there is no parallelism in it. So there were lots of tweaks made to this instruction set so that you actually, when you run one machine and when you run another one with the same code in the same state, you always get the same result. Randomness is taken out of the equation, right? So we created essentially two solutions for you to use our execution environment for convenience. Of course, you can get our machine and plug it on another blockchain and use it as a layer one. But we figured the best way to start it is by creating a rollup. So we created this framework that allows you to create rollups by sending a transaction to the layer one. This transaction data is sent as input to Cartesi, which processes whatever it has to process. It settles on the layer one again, and you can read its state. So for better clarity, Cartesi is not a blockchain. Cartesi is a whole set of tools that you can use, being the basic tool, the Cartesi machine, and the Cartesi rollup is a framework for you to create rollups in the form of app chains. How come? Well, this is a simple example that I like to show. Here, you can send a transaction to the L1, right? This transaction, it will be directed to an app chain. So let's say you have two applications that run leveraging Cartesi. One is a game, and the other one is a machine learning application done with PyTorch. So every input that is directed to the game will run in the Cartesi nodes that is running just that game. And those nodes, they verify each other. But they do not compete with resources with the nodes that are running the machine learning application. So any input that is sent to those nodes is run straight on those nodes and settle on the layer one. And the same thing for the machine learning application. That means, and that is very important, that you are creating essentially what we call an app chain of that specific application, right? It's a layer two that runs just one specific app. And that's very cool because this is how you avoid competing for resources. Of course, there are other things that we can do with it as well. Like we integrated Avail and Espresso to the solution. And you can use those two as data availability and sequencing. So you can have faster finality and of course, all the other advantages that these environments take for you. So in this case, you send the transaction to this sequencing data availability solution. Those arrive as an input. There's a commitment from them on the base layer, and Cartesi settles once again on Ethereum, which is pretty nice because then you're using the best finality possible, the best data availability possible, and it's very cheap. You're using the best execution environment, and you are taking the security guarantees of Ethereum. Okay, so there are two parts for this Cartesi rollup solution, essentially, that I mentioned. One of them is the app-specific rollups. They give your app a full CPU. So it's like unbounded computation. You can take all the advantage of the machine that is hosting. You do not compete for resources. So theoretically, applications are running in parallel in some sense. If I create a game and someone else create the machine learning application, they won't be competing with each other, which is very nice. And the second part, of course, is this expressive general purpose execution environment. Because it runs Linux, it is compatible with every language that exists. It is compatible with most libraries that exist. And this is something that is not mentioned that much, right? We could run the languages directly on RISC-V without Linux, but then you lose some advantages of it, right? There's something that's called freestanding computation of the language, which is just running the language script. But then you lose access to cool things like file system, databases, libraries, and everything else. So rollups is the first solution that you can use for using our execution environment, and it's pretty cool. The second one is called the Cartesi Coprocessor. A coprocessor is something that you, of course, use to assist your main processor. So in this case, we do not create nodes of the application and leave them running, and all of them are constantly verifying each other and waiting for inputs. The coprocessor is something that assists another application. It's just like an assistant for you. So you can create an application that sends inputs to Ethereum, and your whole application is running in here. But sometimes you need to perform or calculate something that is very complex. Like you have to run some very complex math on your application. Then you can send this input to EigenLayer, and EigenLayer will spin up multiple nodes of Cartesi that will all process that single computation, return the result, and this will be sent as a callback. And then all these nodes from Cartesi will be shut down. They are stateless. They are kind of like serverless. So in a sense, it's similar to what AWS does with Lambda, right? You can think of both of our solutions, like one is a serverful, like a REST application, and the other one is a serverless application. And in this case, just like the other one, you have many nodes competing, and they will all calculate and compute whatever is needed to compute, return the result to Eigen, which will perform a callback to Ethereum. This is very cool because you have instant finality. As soon as this computing is done, the result is sent back, and you do not have to wait any grace period to be able to calculate if anyone was actually cheating on the computations or not. This is actually guaranteed by Eigen's security, financial security. So either there is a consensus here, or there is a dispute mechanism that happens afterward, and whoever cheated or whoever lied has their assets taken from them. So everyone is guaranteed to, so your computations are guaranteed to perform correctly, because otherwise people will have their resources cut from them. And yes, this works very well. So what you can build with all of this, right? What is interesting that you can actually build with Cartesi? And there are some apps that I would like to showcase to you. The first one is, of course, okay, so before that, let's understand what kinds of things you can build when you improve your computational capacity, right? If we are talking just about computational capacity, if you are using Ethereum layer 1, you will never be able to do things that are more complex than token sales and regular DeFi. And then when you start playing around with EVM rollups, you can start doing more complex DAOs because you can have more computation, you have less cost per each transaction, so you can start making applications that receive lots of inputs, but they cannot compute complex, really complex stuff. Otherwise, they get stuck and computation gets very expensive. But when you're using an app chain rollup that is not taking away from the whole network, then you can start creating decentralized, massive multiplayer games. You can start to create decentralized social networks. You can start creating even and executing even AI algorithms on chain. You can create world simulators, and we're gonna see all of that here, right? So the first game that I like to show you is called Bubble Wars. It has an on-chain physics engine. So it has a strength that propels your token forward. And whenever it hits someone else, it actually engulfs them and steals their assets. So it's a game where you deposit some assets, and you're trying to steal assets from everyone else. This wouldn't be able to compute in Ethereum because the speed and the direction is all physically calculated on chain. So yeah, this is very nice. And this is the first concept that I think of an MMO that would work really, really well on chain. So talking about other kinds of games, there is also World Tycoon. World Tycoon is a really, really fun game. They just received a grant from us and just finished this grant. If you ever heard of SimCity, it's actually SimCity on chain. You start a deposit and you start creating your own city, and you can either win a lot of money by playing, or you can lose a lot of money by playing. So it's actually SimCity with real stakes, and that's really nice. And it's really the whole the whole game created on Web3. I've never seen any other Web3 game this complex actually existing and actually working. You can create social dApps. There are two that I really like, which are called Comet. It's a co-creation platform for poems and texts. So people can write whatever they want, and they create a poem together, or a story, or lyrics for a song. And people who mint this NFT, they actually pay the creators, and there is a whole logic of distributing the gains and whatever was gained for that NFT. So it's really nice, and it's interactive, and it's fast, and you wouldn't be able to perform the mathematical calculations to share the assets without some powerful environment. And then drawing canvas, in which it's actually a drawing platform, but people can paint on top of other people's drawings. And whenever they do, they can mint this drawing together and once again share revenue, and all the drawing is verified on chain. So you're not just uploading an image, you are uploading the steps you took to draw that image, so people can verify that you actually painted that instead of just stealing the image from someone else. You actually performed all the strokes to develop it. It's on beta right now. You probably can check it out on drawingcanvas.io, and it's really fun. There are also machine learning solutions as a proof of concept that we created. So biometrics and iris classifier are very famous data sets that are used for machine learning. And those are and those work really fast and really well. So you can start using linear regression, KNN, very famous machine learning algorithms that run on chain. And there is a project that is in alpha called Lilium that allows you to verify environmental details of pictures to track the generation of carbon credit given specific trees and specific lots of land. So people can actually compensate for their carbon generation with on-chain verifiability, which is very nice. So there is this whole website called Rollup Lab, in which you can explore what's being built with Cartesi. And it's actually really fun because you can see many different kinds of applications that are created. There are lots of games, there are lots of machine learning solutions, there are lots of DeFi solutions. And please check it out later. It's very, very, very cool. And it's also important to say that we have a Udemy course in which you can understand step-by-step how to code for Cartesi and start your journey, understand every one of the intricate concepts, or join our Discord to talk to the community and better understand any doubts or any questions that you have. I would very much like to make a demo to you guys. So I'm just gonna stop the screen share real quick, and I'm gonna share my entire screen here. Just give me 1 second. So this is the desktop that I have to share. Okay, so now you're seeing my full desktop, and just to show to you guys how quick it is to develop with Cartesi, we have created the CLI. Oops, let me just clear here. We have created this CLI, and you can just perform a Cartesi create my app and select the template. So in here, I'm going to create an application with Python, for example. So I'm going to cd into, whoops. into my app, and I'm gonna open it on Visual Studio Code for you to see the structure of the project as a whole. So it's a very simple application. In here, we have the Docker file that builds Linux. You rarely have to touch on this. And this is where the magic happens, right? Is in this dep.py right here. In here, you can see we have two functions, handle advance and handle inspect. These are akin to post and get methods of Web 2, but this is actually what happens whenever you sign a transaction. You arrive in here, and whenever you want to make a getter to just read the state of your app, right? So anything that you're doing, you're executing here, and you are creating here. So let me just try to show you how to build the application. I'm gonna run a command called Cartesi build, and this will build my Cartesi machine. The first time you build it, it might actually take a few seconds. So while this happens, but actually it ran faster than expected. So whenever you get a confirmation of the machine being actually built, you get this symbol here, and it shows the number of cycles that were ran. And now I can perform Cartesi run, which will spin up all of my Docker containers. And it will create my application and start running my application. I already had a Cartesi application running, so I had a conflict of port here. So I'm just gonna stop it and run it again. Okay. This will actually spin up a local chain, and it will actually run my application on top of it. I can here access the Explorer, which is basically a blockchain explorer in itself, and send transactions to my application. So let's say I want to send a raw input to the application with some text. Let me go to string to hex converter, say hello world. And this is the input I'm gonna send to my application as a raw input. I'll convert transaction. I get the transaction confirmation. The input was sent successfully. And my application here will say that we'll print the exact line, received advanced request data with the payload data that I sent. So whatever I want to compute, whatever I want to execute, I can just execute here. I can perform changes on this content that came. And if we go to the hex to string, we're gonna see that it was exactly the hello world that was sent. So I can just decode the content here and perform whatever computation I want with it. It's really fast, it's really simple. It's Python, it's Go, it's Rust, it's whatever language that you actually want. And this works really well, it works really fine, and it's much faster and powerful and flexible than Solidity in itself. So I'm gonna go back here to the presentation, to the first slide. And yes, if you guys have any questions or any doubts, I would love to take them.
I have a question. In the Solidity, we use ABI application binary interface to interact with other smart contracts. But on the every application is a rollup. Is that okay? Is that right? Then if we want interact with another application rollup, is there any way
Yes.
so
So
so we also
every
have something like application boundary interface.
yes, that's actually a very good question. Let me just get a code in here real quick of an application I was just doing for tests. Here it is. Okay, so this is an application I was creating in here, and there are some things that are very interesting to show. There are three main kinds of outputs that you can create inside an application, right? A Cartesi application. The reports, which is just a report for something that happened. It's not a verifiable output. The notice, that is the verifiable output that you can check on chain if it's correct or not. And then there is the voucher, which is an application that allows you to interact with another smart contract that already exists, right? So once again, let me go here to the dashboard and stop the application I'm running, and I'm gonna run this other application that I already built. So in here, I have this application. Let me just explain to you what it does, and you're gonna be able to see how it can interact back with applications that are not inside the rollup, right? So this is an application that is a calculator. I don't know if you have seen Twitter lately, but there's this huge discussion of if 100 men could beat a gorilla on a fight. So I created a calculator that given a person, you can actually calculate if a gorilla, how many would be needed to defeat a gorilla, right? This is the whole fighting algorithm. We can skip that logic, but the important part is this part here, which is called emit voucher, which allows you to interact with other smart contracts. In here, you can see that I'm sending a payload to this destination in here, right? This destination is a specific smart contract. So I'm gonna call the function mint in the smart contract with this address right here. Let me put it here for a matter of clarity. So I'm gonna call the function mint to mint an NFT in this smart contract here with this address and with this data. Okay, so let me just run Cartesi run, and you can see that I will be calling the ABI. This is essentially a very minimalistic part of the ABI that I'll be calling. So the first thing is this is the contract, and then I have here a Gorilla contract that basically has an NFT, and I will be calling from my rollup this exact function, which is called mint. So I'm gonna be creating this NFT with this data. And then I'm gonna be reading the data for you to see that it actually works. So first thing I have to do is, actually I have to run it with a flag here because the rollup has a finality period, right? So I have to pass a flag in here saying what is the finality time that I need. Okay, so epoch length 1. All right, now I'm gonna deploy the contract. And you can see that I deployed the contract at this exact address. which is the address that I refer here in the application, right? Now that the application is running, I want to send this. I want to send this as an input, and just so you can see what is the input I'm sending, I have a test call here. This is the input I'm sending. I'm sending basically a JSON with a name, an age, a height, and weight. So the description of that person who will be fighting the gorilla. And I'm gonna send it as input. Okay, so going back here to, going back here to the code, you can see that I received the input. It's in here. This is the exact input I received. I opened the data and I created a notice, which is one kind of output, and a voucher, which is another kind of output. And the voucher contains this data in here. So for my notice, I said estimated number, let me increase here, estimated number of Joãos, me, needed to defeat the gorilla, 39. Fighters who died in the process, 28. So if I go here to the vouchers field, I can actually see that a voucher was created, and I can actually execute this voucher. So right before executing the voucher, let's see the value that is in the NFT number 1. Whoops. Something weird happened. Guess this terminal is bugging a little bit. Okay, so you can see that is basically a blank data in here, which where I have essentially no information, right? But once I execute this voucher, I'm gonna interact back with a smart contract in the base layer. So I'm gonna get the output, and now I have content in the smart contract. So this here is the response for this get token data, right? So I'm getting the name, the number needed, and the number following. If we get an ABI decoder here, I can assure you that this is a string and 206, and I will be able to see that João, and this is actually the numbers that were, these are exactly the number of, that is answered here, right? 39 fighters and 28 died in the process. 27 in hexadecimal is 39, and 1C in hexadecimal is 28. So you can actually communicate with a smart contract that is on the base layer. So to communicate one rollup with another, you essentially execute this kind of output that communicates to the base layer, and then the base layer will send another input to the other rollup. So you can communicate rollups with each other. With the coprocessor, this is even faster because you don't even have to execute the data. For the coprocessor, you can see here, I have this documentation page, Cartesi Coprocessor, development. And the coprocessor smart contract is much simpler, in which, let me get it here, the link. Is it under test? No. So this is an example of a smart contract that runs the coprocessor, right? It has this function run execution where you call the coprocessor, and then it executes whatever is in your Python code or your Java code that you deployed elsewhere. And the result comes for the handle notice. So once again, you're working on Solidity. And in here, you're gonna be able to use the ABI to call to talk to any other application that you want. So it's even more straightforward. Does that make sense?
Okay, cool. I have another confused. Can you show your a PPT on the about the first half on your PPT? I have a question about why why get the input from the Esri? For example, like OP stack, they get input from directly from the user instead from the Esri.
Oh, yeah. Okay.
I have some confusion about this.
Yeah, so this is mostly for convenience that we put the inputs on this input box smart contract that comes from the base layer. It doesn't need to be there. It can work in other ways as well. This is just one way we designed the framework.
Okay.
But for example, if we go back to the presentation in here, let me find it. In this slide, right? It's here somewhere. Here.
Yeah.
So
okay.
In general, the transaction comes from the base layer, right? But in OP stack, it does not come from the base layer. It comes from somewhere else. So yeah. In this design right here, this is a simplified version of it. But in this case, the input actually goes to a convenience layer called transaction manager through a type of input called EIP for what was the EIP again? 712, EIP 712, right? So you actually send the data directly to the node, and it registers the data in whatever sequencer that you want to afterwards. So this way we there are lots of reasons for why we did using the base layer. It's one possibility that is simpler, that does not enforce you to use another base layer. And then you are fully trusting and you're fully inheriting the security of the base layer when it's coming through the base layer directly. But you can send it directly to the node in here. And then after sending it to the Cartesi node, it will send to the sequencer, which will spread to the other nodes of the rollup. But it was just an option to guarantee that we're inheriting the security both when using Ethereum as DA and as a settlement layer. So this way, nobody can contest that the Cartesi design allows you to fake the consensus, I guess.
Oh, okay. Anyone have question?
Hey, hello. This is Kunver speaking. I have a question, Ro.
Yes, please.
Just now you have mentioned the machine learning part, and you mentioned an example, for example, the iris test. Can you show us more details about that?
Yeah, of course. I can. I don't have it cloned here, but let me just go in here. The iris is a very interesting solution, actually. Here, iris classifier. So the iris is a very interesting solution, actually, because it was done with, if I'm not mistaken, machine to code generation. No, it was actually with cross compilation. All right. So this one here, it's essentially the database, the data set that you get in scikit-learn. So data used for this example can be found right here. Whoops. Okay, this is that, my bad. But it's essentially a KNN classification algorithm. Are you familiar with how KNN works?
Yes, I know. And my question is, where you deploy the model, for example, where you deploy the KNN model and where you put your data set?
Yeah, okay, so the model, just remember when I showed you this right here. Essentially think that there is a model running in each of these nodes in here, this PyTorch nodes. Each one of them has the model running, right? So it's basically an API, just like this code in here, where you have handle advance. And in here, you will have the run model for the KNN. It's pretty straightforward. You pre-train the model, and then you add it here. Let me show you the code of the iris classifier. This, I think, is, yes, that's it, KNN classifier. So this is the CSV with the data set of the iris. And this is the knn.py. So essentially what we do is we load the CSV, we convert the data set, and the data set is spread through the KNN sheet. And then the Euclidean distance is calculated and get nearest neighbors is run. It's pretty straightforward. It's just, it just arrives in here. Let me, in the handle advance, reads the input, opens the input, and then runs the KNN classify function, just like whenever we're using scikit or anything. This is actually hard coded in here, but you could just use scikit-learn, I guess. I don't remember why the creator didn't do it like this, but yeah, it's just straight up run in Python code. If you want, I can share this link with you, I guess, and you can explore it. But this is the entry endpoint for the model, and this is the function where the KNN model is running to get nearest neighbors, and it calculates the distance of each.
Okay, thank you. I will check the details later. Thank you very much.
Thank you.
Is anyone have more question? 大家也可以用中文，也可以。我可以尝试着帮大家翻译一下，如果你有中文问题的话，有没有？Since no more question, Joshua, thank you. Since no more question, that's all.
All right. That's awesome, guys. Thank you very much.
Thank you. Thank you.
Thank you very much for the opportunity in speaking here. It was really nice and love meeting you guys.
Bye.
Bye bye.
Bye. Thank you. Bye bye.